Merci François, et je vais introduire, I will introduce now Christophe Justino. So Christophe is a material engineer, so not a geotechnical engineer. He's the first material engineer since the beginning of the seminar. And he graduated from Polytech Paris some years ago, and he's been 18 years in the material department of Soletange-Bachy. With various roles, but he's also involved very much for the profession. He's member of several standardization committee in France and in Europe. He's the co-leader of the Tremy Concrete Guide, European Tremy Concrete Guide, that was translated in French by the SOFONS and the CFMS. And he's also leading a new guide on drilling fluid and the interaction between the drilling fluid and the concrete. Thanks, Christophe.
Okay. Thank you, Serge. So, as I choose to do the slides in French, I'm going to speak in English. Okay, so I was told to talk about concrete in a geotechnical symposium. So, obviously, we are going to go a little bit out. Link with Coulomb. Okay, we all can apply the more Coulomb theory to concrete. It's possible. We'll see that when it comes to durability indicators, we can use the other part of the work from Coulomb, because we can measure the charge, electrical charge passing through the concrete, and it gives us an idea of the ability of the concrete to resist to penetration of chlorides. And it's very important because one of the first role of the concrete is protect the reinforcement. Once we've said that, the only main purpose of my presentation today is to show you that concrete in geotechnics is a very specific part of the concrete technology, and that in order to adapt to what François showed you, the change in the dimension of the elements, the retaining structure that we need to build in for piles and D-wall, we are going deeper. We are asked to produce higher strength concrete, and concrete technology has evolved in order to allow that, more durable concrete. But when it comes to geotechnics and the way we have to place the concrete, it requires for us to also be innovative in the way we specify and the way we characterize concrete. And that's a little bit of this review that I'm going to present to you today. Okay, so there is also a lot of pictures, very few equations. We are not going to design a concrete mix today or going too deep, but it's just to give you an overview on what has changed. Okay, so we need to start a little bit with history, because initially I wanted just to give you some kind of history of concrete, but recently I was spammed with a lot of email from the sorry. So François, it's not you. It's just I can tell that it's just a magic. Okay, it's a way to go quicker. Okay, le béton Roman Empire concrete. So you might have seen that. So I saw rather than speaking about history, just saying that I've been spammed with all my colleagues because they know that I'm lead of materials for Soletange, and say, but why aren't we using this self-healing Roman concrete? Is it something new for us? So I wanted just to take the opportunity to say that yes, Roman concrete was very durable because we can still see structure. But on all the articles that I've seen about that, there was a mention that is important. It's saying that nowadays the concrete we are using, is more durable than Roman concrete, and this is for all the reasons I'm going to show you, because there is standard, there is a specification on concrete. So yes, Roman concrete was very good. It was in a way not using Portland cement because it was not existing, but it was using the same principle, quick lime, pozzolan, so all the kind of thing that we are using now. It was not necessarily lower carbon emission than what we are using, but it was interesting to say that it exists. Astonishingly, between the antiques and the 18th century, there was no concrete, let's say. It was rediscovered. And the discovery of concrete obviously allowed a lot of development up to now pre-stressed concrete, very high performance concrete that allow us to do retaining structure with reinforced concrete, with going very deep. And the last thing that is like the chart is what I wanted to do is that keep in mind that concrete nowadays, it's governed by specification. There is a lot of standard on all the constituents for concrete. And that's also the reason why we can produce now more durable concrete and higher performance concrete. Okay, so now if we go to concrete in geotechniques, in order to explain why it's so specific concrete in geotechnique, we need just to go back on the way we pour concrete. So we have some slides just to re-explain. For those who are not specialized in this kind of diaphragmal deep foundation concrete, once we have used the magnificent tools, hydrophrase, grabs, in order to go as deep as the project requires, that we have perfectly controlled the support fluid with the nice also equipment, and that we have put in place the reinforcement into the trench. We use a tremie pipe that goes at the bottom of the excavation, and we pour the concrete from the base to the top. So that requires, as it was explained by François, that the concrete that we are pouring needs to be maintain its workability, its fluid properties for a certain amount of time. You mentioned 10 hours. We have example of projects where we had pours that could last for 18, 20 hours to pour 1,400 cubic meter in just one lift. So that means that the concrete has a very good requirement. On top of that, we are blind because we are pouring concrete under support fluid. So it's just an overview of what can happen. So on the left side, we have what happens when everything is perfect. You can see the transition between the support fluid in brown and the gray concrete. But if we are messing with the properties of the concrete or the way we pour, we have an intermixing. The concrete is washed out at the base, at the top, and it leads to defects. The problem is that in that case, the defects will only be seen when the box is excavated, and you can imagine the impact on repair. So that's why concrete is an essential part of the success of those projects. Okay, so, and just to emphasize, just a view on how the concrete is poured. So that means that in order to, this kind of concrete, it has to be like close to self-compacting concrete. It has to self-level. It's not vibrated, which is the case for civil works. We do not vibrate. It has to be pumpable, very workable. As I said, we see that we need to maintain its workability from minimum 3 hours, but up to 10 hours in some circumstances. So in order to do that, we need to deal with obviously the constituents of the concrete, but as for every concrete, so we're still dealing with aggregates, cement, cementitious materials, admixtures, and we need to consider different aspects of the fresh property. So one is the concept of rheology of concrete. So there's a need to understand perfectly the different type of physics behind the rheology of concrete, meaning that it's a mix between what we call the seuil d'écoulement, it's the yield of the concrete, and the viscosity of the concrete. With the concept of rheology, we can access the consistency, the workability retention, and another key parameter that was not really a focus, let's say, before 2000, which is the stability, meaning that we are, you imagine you have 70 meters of fresh concrete. There is a lot of pressure under the concrete, so concrete tends to bleed. Some water of the concrete tends to go out, but when it comes to being pressure, it can do massive damage if the mix design is not balanced properly, and we can have like these very high channels of water coming out of the concrete, washing out the concrete, and impacting its durability. So with that, we need to have a concrete that can be placed under a support fluid without washing out, being able to pass through reinforcement that are more and more dense due to the high requirements of the project. So more and more we have to be able to have concrete being able to pass through very dense reinforcement without vibration again. And it has to be stable, as I said, and resist to pressure. So there is a lot of constraint that can't be dealt with, let's say, what I would say traditional concrete. Sorry for the mic. Okay, so generally it's well accepted that before, let's say, 2000, it was really typical to have what we call three-component concrete. So meaning that the properties of the concrete was driven by the dosage of cement to get the strength, by the water content to get the fluidity and the balance between gravel and sand. In order to be able to face the challenges of more durable concrete, more flowable concrete, higher strength concrete, the industry has moved to what we call generally 5-component concrete, where we enter the era of admixtures. And the admixtures helps to reduce the water and get higher strength. But at the same time, by reducing the water, they give you more sensitive concrete to variation. And as the concrete is more sensitive, and especially for geotechnical concrete, it was not enough to just test what we call the slump and the strength, because it was not enough to fully characterize the concrete that we need to do to pour concrete at 70 meter depth. So since the 2010, let's say, a lot of development have been made through different standard committees, through technical working groups like the one that are led from the EFFC, in order to, let's say, develop new tests, first to characterize the stability of concrete. So we'll see that tests have been developed to measure the ability of concrete to retain its water. Also to, let's say, have simple tool on site to control the viscosity, because we cannot use a rheometer in site, and it's a good tool for laboratory, but on site we need to have other tools. So just by using simple tools that I'm going to detail, we are now able to characterize the yield of the concrete and the viscosity of the concrete. At the same time, we are more and more challenged about durability requirements, so we need also to develop tools in order to be able to explain how the concrete places itself in the soil. So we have more and more numerical modeling of the way the concrete places itself in order to answer one of the fundamental questions of pouring concrete is the first concrete that I'm pouring at the base, will it go up to the top, or will it stay at the base, or will it be mixing with the other loads? So through numerical modeling, we have been able to approach that and to rationalize. And typically, for example, for the pours that were lasting 20 hours in London for deep shaft, we never use a concrete that has 20 hours of workability retention, because it would have led to a huge problem in terms of setting time. But we were able to pour 20-hour pour with 8-hour workability retention concrete. And we demonstrate that it was working through modeling. Other issue, we are speaking about 2.4 meter D-walls, for example, in Japan. So that means that geotechnical concrete, we are facing the same issue as mass concrete. So the heat of hydration of the cement can build high temperature within the core. And we have been also, there was a need to develop modeling and numerical tools to, let's say, predict and also to control on site the temperature in the very large pore. So just imagine, when I arrived in 2005, the only thing we were doing in concrete for D-walls and piles was a slump and cylinders to test the compressive strength. Now we have, like, in France, let's say, most of the contractors are using at least 5 different testing on concrete. If you go in UK or other countries, sometimes you have a list of 10 tests. So not saying that 10 is too much, but the 4 or 5 that we have retained and that we have put into standard in France are really a change and help to increase the quality of the concrete we are building. Last but not least, our challenge, because we are following the trend in concrete, is performance-based approach on concrete, meaning designing concrete not according to prescribed mix from the standard, but based on the durability indicators. And this is the next step, which is going to this transition to lower carbon emission of concrete. So we have a role to, we need to look at that in geotechnical concrete. And that's why, for example, companies like Soletanche-Bachy have their policy or their way to engage into that. So Exegi, for example, by Soletanche-Bachy is all the consideration we are taking in the mixed design of the concrete in order to optimize and lower the CO2 impact by replacing Portland cement by other additives. So the next part is very quick. It's just for you to follow up. Important to understand, we are not going through all this, but know that the concrete standard has changed, national annex this year. And the main change in this national annex is introducing the possibility to use recycled aggregate from concrete deconstruction and to use the performance-based approach to design concrete, meaning that your concrete mix design will be validated based on durability testing and no longer based on the minimum cement content or maximum water cement ratio. And specifically for geotechnical concrete, we have added the additional tests that have been passed into standard. And those tests mainly are the flow table, the slump flow, which allow you to have a direct vision of the stability of the concrete, detect whether or not the concrete is segregating. The flow cone, which is like something like the flow cone for grouts, just measuring the time to empty a Abrams cone to get a feel on the viscosity of concrete. It's a major impact because above the limit value that we have, generally, it can change from, let's say, discharging a 8 cubic meter truck in 5-10 minutes to discharge a 8 cubic meter truck in 30 minutes, 45 minutes, just because of the viscosity of concrete. So those are important tools. Stability test, bleeding test, that helps you to measure the ability of concrete to retain its water. So in more detail, for stability, we have a suite of tests that, it's a very simple cell that we put into pressure, and we have threshold value of the maximum water that should be let out. It's a very simple test that lasts 5 minutes. A test that duration a little bit longer because it's at atmospheric pressure, but very interesting to identify the potential for bleed channels. Those tests are typically tests that are recommended to be done before the project starts, when we do construction trial. It looks very simple. It's very simple, but it really can change the thing on concrete. The performance-based approach, it's another step. So as I said, now when you design a concrete according to the concrete standard for structural concrete, you can decide to go on the prescriptive approach. But if you want to optimize your mix and try to reduce the cement content in your concrete for economical reason, for technical reason, for example, for sustainability approach, there is now a framework that is existing in France, and France is one of the first countries that has built a documentation, a standard that allow you to go to this direction. So I'm going to pass just to explain you and for each of the exposure class that you are facing, you will have a dedicated test with a standard associated. For carbonation, we have accelerated carbonation, porosity, resistivity. For corrosion due to chloride, there is a chloride migration test. And even for chemical attack that we are always facing in geotechnical concrete, because we are in the soil and most of the time we can have sulfate from the soil or things like that. we have those tests to test the risk of low pH or the impact of sulfate in order to demonstrate that the alternative mix, which is, let's say, optimized from the prescriptive approach, will give you the right concrete for your project. Okay, so that's just to show how it works. Okay, so just to emphasize the interest is that normally we can use the normative approach. We have a range of cement, but the binder content is imposed, the water cement ratio is imposed. There is restriction on the replacement that we can use, all those cementitious material like slag, fly ash, silica fume, calcine clay, limestone filler. We have limitation. Now on the performance-based approach, we have much more room to play on the replacement of standard cement with those additions, and it allows you through validation of a durability indicator to build a new mix design. Apart from that, there is a lot of new innovative components for concrete. Need to keep in mind that at this stage, they are, let's say, not according to standard. So using those products need European technical agreement. But there is a start, even in geotechnical concrete, to see alkali-activated geopolymer concrete being used. Okay, well, this one is for you. I will just finish just to keep you informed of what is going on in terms of concrete. It's how complex it gets, but we went from a prescriptive approach. In 2022, we released the performance-based approach in standard. And the work now being done at the standard committee for concrete, there is a group of experts working on what we call low carbon solution. And there is, it's in interaction with Eurocode 2, with the standard committee. And the idea is to identify all the steps that we need to climb, let's say, or to pass in order to continue to decarbonize the concrete industry. That's giving framework to new materials that have a lower carbon footprint than Portland cement. That's giving like a terminology, a way to define what is low carbon concrete to avoid going to greenwashing, for example. And also linked with the Eurocode is how to, let's say, not just focus on the concrete material itself, the mix design, but the overall structure. So those are the next challenge for the future. And I thank you. I finished now.
Thank you, Christophe. Any? Well, hello. Yeah, works. Good. So, well. Any questions there? We have our specialist question. You know the name? He's got a question anytime.
Yeah, thank you. I'm just curious. What is the ideal relative density between the mud and the cement?
The standard explains. Yeah, so sorry. So,
Or the standard, yes.
So, in reality, when you go back to the old documentation, it's not really the difference of density between the mud and the concrete that matters. But though the maximum density is 1.15, in some occasion we can relax to 1.20. But when you look at there is this Syria document from the 80s, early 80s, explaining you that what is more important is the contrast between the yield of the concrete and the yield of your support fluid. That's what is more important, because you need to ensure that when you pour the concrete, that this concrete has enough strength to put in motion the support fluid. And it's not a matter of density, in fact. So the biggest risk you have is that if your support fluid that is remaining still in the trench start to gain gelling, let's say, is when it gets to a certain yield that is so gel that when the concrete is being poured, you have not been able to put into motion. In that case, you will have much more risk of intermixing rather than working with a density of 120, 130 when your concrete is 2.4. So we have, let's say, in the standard limits on the density for the support fluid, but for me it's not really the point is not to have the best let's say exchange. It's more for other reasons like risk of sedimentation or things like that.
And another short one today, the 25 megapascals compressive strength is still the norm, or what is the value?
So there are two questions in your... one could be answered by Nicolas, is the 25 megapascal still the standard for calculation? So that's one thing, no. The other thing is that...
What is it then?
So anyway, for concrete, the way the standard exists for concrete is that strength is part of the durability requirement. So that means that most of the time what I see on piles and D-walls is that even if you need 25 or 30 MPa for the calculation of the structure, depending on the exposure class and the aggressivity of the soil, you might have to design a C40, up to a C40, and you are not using all these strengths for the calculation, but for the durability. And that's the main interest of the performance-based approach, because now we have a way maybe to avoid over-designing a concrete in terms of strength, when in reality for the design we are not using these strengths. So that's a way.
You can stay. Another question.
Just a small question. I know that we are all artists. So as an artist, I have just a question about the final aspect of the wall after excavation. So we have many jobs with architects that are afraid of what will be the aspect. So in definition of the concrete, the constituent, so is that a parameter that you can take into account, or no? You'll see what you get, and we have to wait for final result.
We are casting the concrete against the ground. So when you look at let's say when it comes to surface finishing, obviously for civil works, there is a lot to do with the concrete mix design, but there is also a lot to do with the formwork, okay, the finishing. So in our case, even if obviously what we are going to do is to avoid bleed. So avoiding bleed will avoid as much as possible this aspect of channels at the surface. But because of the way it's cast against the ground, it's as cast, so it's complex to work on the surface finishing like that. So after it's you need to put if you really want something better, you need to put a precast thing. I've seen architects. I know stories that where architects were so amazed by the way the D-wall, for example, aspect was, or even I've seen an architect very blazed and glazed by channels in the walls. So you can be artist and you can also have very eccentric ideas, let's say, and we can hope for that.
Thank you.